Next part of our lecture is going to be about electric field. An electric field is another explanation of electric forces, and it's similar to gravitational field near an isolated mass. So it's just something exists. Maybe it's you can think about it this way: if you near the earth and if you drop the ball, the ball is going to drop down to the earth, and the interaction between the ball and the earth happens through gravitational field. Similar way, if you have big electric charge, let's say positive, and you place tiny electron next to this big positive charge, electron is going to be attracted and it's going to move toward this positive charge. So this interaction happens through electric field. One of the ways to represent electric field is to use those arrows. Look at this picture. And this picture represents a positive charge in the center, and electric field is the lines, positive lines radiating away from the positive charge. Electric field is a vector and is denoted just by letter E, electric field, with a vector sign on top, just like that. And when we're making a picture for electric field lines, if we have a negative charge, like over here, negative Q, electric field lines are toward the charge. I'm just repeating what's already in the picture. And if it's a positive charge, the fields are going to go away from it. That's pretty much it. Negative charge toward. And we try to do it symmetrically. And this is electric field lines picture. Electric field and a test charge. So how we can test for electric field, and that's why it's kind of useful. Sometimes we don't really know what created electric field line, but we know it exists because if we place a test charge in the field, we can map what force this charge experiences. So let's say if the charge Q is placed at the point anywhere in the field and it experiences the force F, so electric field at this point is equal, can be found using this formula. By measuring the force on the test charge, the magnitude and direction of electric field can be verified. This is usually done when we don't really know what's creating electric field. Electric force that the charge is going to experience in electric field is going to be either parallel to electric field lines if charge is positive, or it can be in the opposite direction if Q is negative. So we can look at it this way. If this is an electric field lines, and we would place charge, positive charge, then the force this charge is experiencing is going to go this way. And if I would take a negative charge, then the force it's going to experience in this electric field is going to go opposite direction. It's going to go this way. So units for electric field are newtons per coulomb. Nothing special here, just newtons over coulombs. And given point charge, we can calculate electric field using Coulomb's law, where Coulomb's law is just charge Q, little q is a test charge, and definition of electric field is F is equal Q times E, hence dividing force by Q, we can calculate that electric field of point charge is equal constant K, this charge Q over R squared. This is how magnitude of electric field changes for point charge. Electric field, quick summary. Direction of the electric field is always along the line connecting the charge producing the field to the point where a field is measured. Electric field is always directed away from positive charges, and electric field is directed always toward negative charges. Importance of the electric field. Electric field is present even when there is no test charge present to experience the electric force. Any charge or collection of charges will produce an electric field. It also helps us explain how the Coulomb force can act between two charges that are separated by large distances. They interact through the field. It also is essential for understanding lots of other principles of electromagnetic theory, including waves. We already used electric field lines and showing the field lines of a point charge, but if you have a combination of charges, then the line could be not just a straight line, could be something wiggly, like in these pictures. And this is just another way to visualize electric field lines. Field lines are a set of continuous lines that are always parallel to the electric field. Basically, if you place an electric charge positive over here, the force it's going to experience is going to go exactly like that. Over here, the force is going to experience is going to be this way. Over here, this way. So that's what electric field line represents. Let's look at examples of the electric field lines. Given positive charge, electric field lines going away from the charge, like in this picture, and for the negative charge, electric field is supposed to go toward the charge. If we place positive charge and negative next to each other, the electric field lines are going to be bended, and we're going to have something like that. The schematic representation of electric field doesn't really give us strength of electric field. It gives us direction. However, we can kind of estimate if electric field is strong or weak by just looking at the density of the electric field lines. So if I would have a picture like that, or picture like that, and this next to each other, you can say that electric field here on top is going to be weaker than electric field B. So electric field B is stronger than electric field point A because there is more lines. The lines are denser here than here. To find electric field that been created by multiple charges, as on the previous slide, we'll need to use a principle of superposition, and we need to use vector addition. So you need to first find electric field due to each charge and then add them as vectors. When we draw electric field lines, we must obey certain rules. Field lines always begin on a positive charges. Field lines must always end on negative charges. Electric field lines also obey the superposition principle. That means we have to add them as vectors. Let's try to play around, make a simple example. Move that away, and let's just do negative charge here, positive charge here. Let's look at this point in space. We would have electric field going toward negative charge and away from positive charge, about this way. Let's see, it's not really a good one. Let's try a little bit better. This better? Well, kind of. So now how do we add them head to tail? We have to move this vector over here, and then vector addition head to tail. So this is resultant. So this is in this particular point, electric field line is going to look like this blue vector. Problem 15 from a textbook. 4-point particles are located at the centers of a square. The 2 particles on the left each carry charge plus Q. If the electric field at the center of the square, that means here, is directed to the right along x plus axis, that means this way, what might the charges on the particles on the right be? So charge here, question mark, charge here, question mark. This is just conceptual problem. You don't need to do much calculations here, but you need to understand what's happening. Let's just make this small picture, move it over here, and let's try to work over here. So what do we have? Charge plus Q and plus Q. At the center of a square, they're going to create electric field. This is from the first charge, from a second charge, head to tail. Let's do red color, directed to the right. Okay? So we already agreed with the problem. So if the charges in the right side would be 0, that would be all good. What another charge will work? What if those charges are negative? What will we have? If this one is negative charge, what do we have in the center? It's going toward, and resultant is, again, the same direction. So charges on the right might be also negative. Can they be positive? The answer is yes. As soon as they're small enough that they don't overwhelm this vector. So if resultant from 2 charges on the left is this way, and this would give us, let's use red color here, this way, this way, this way is the resultant. So if this red vector is smaller than black vector, we still have electric field going to the right. So I can say there is 3 possible cases. 1, 0, 2, any negative charge, 3, positive charge but small. Problem 40. For this problem, I would suggest you press pause, think about it by yourself first, and then click play to listen to my solution. This is a very simple problem. The answer is very simple. That was a hint. Go ahead, press pause now. The key to this problem is that the charge is distributed uniformly around the ring. And you don't really need this information. This is just extra. What's happening here? The answer is very, very simple. It's 0. Why is it 0? If we divide this ring on a small charges, it becomes a very symmetrical problem. Look at this charge over here. Electric field created by this charge at the center is going this way. Let's look at the charge opposite to it, this one. Electric field created by this charge goes this way. So those 2 vectors, opposite direction, equal lengths, cancel each other out. In a similar way, you can look at this charge and this charge, this charge and this charge. Contribution of this charge is going to be cancelled by another charge in the solution. The answer is, as I just said, 0. That's it.